Hi students, welcome to this session on finding the magnetic field intensity at any point on the axis of the circular disk. What is the aim of this discussion is we have one circular disk which is placed in the xy plane. See it is assume that it is our room. In that we have kept this disk in floor like that. So this is what our circular disk which is kept at xy plane, that is z is equal to 0 plane. So circular disk is at xy plane, right, where z is equal to 0. Okay, so the first thing we have to know is, and the radius of the disk is rho. Radius of the disk is rho. What is the thing we are going to do is we need to find what is the magnetic field at point P. H at point P. That's what we have to find. Okay, that is the thing we are going to find. What is the magnetic field at this point P? This is the distance at the height of H from the xy plane. So the height is the H. So here you see x0, this point x0, y0, z-axis is H. That's why 0, 0, H. Okay, so what is the logic we are going to use? It is a continuous charge distribution. What is the thing is, we are going to find instead of taking total disk, first we take dl and find what is the magnetic field at this point, then dl2 and find magnetic field at this point, then dl3. Like that you can take you divide total disk into small line segment, current carrying element ideal, and find the magnetic field and integrate it. That is what our aim. I is a current flowing through the disk, right? So what is the assumption we are going to make is current is steady state current, right? So I is steady state. Okay, right, and we are this field is field location in free space. That is, we are going to find magnetic field in free space. That's what our aim. Okay, these are all the things we must know. Now we will see that. Okay, so we know the magnetic field intensity at any point is given by Biot-Savart law. See, this is one of the applications of Biot-Savart law. If they ask any 16-mark question, you can write this only. Okay, so finding the magnetic field at any point on the axis. So we know as per the Biot-Savart law, dH is equal to ideal cross r cap divided by 4 pi r square. This we can write as ideal cross r vector divided by 4 pi r cube. R vector, r unit vector is r vector divided by r. So that's why it is 4 pi r cube. Okay. So next what we have to do, we have to find what is r value, right? So r is, here we have a capital R. So this is capital R. So instead of small r, we can put capital R. That's not an issue, right? Simply. So we can make it as capital R. Okay. Now we find what is R, right? So first, first we find what is R. We know from the diagram, you see this is a cylinder, it is rho, right? So what is that? We know this is arrow direction, it is rho, so it must be in arrow direction. The vector is rho arrow. This is what your R. So rho arrow plus R will give HAZ, right? So you see this, you take this triangle, it is like this. Right, okay, let me draw properly. Right, it is like this. You see, this is what our rho, this is what our H, this is what our R, right? This triangle is, this part is along the direction of arrow. So if you consider this a vector addition, rho is along the direction of arrow as per cylindrical coordinates. So vector addition means this plus this will give this one. If you add this part and this part, you can get this part. That we have to know. So rho arrow plus R gives, what is the height? H. In which direction? AZ direction. It's a vector addition. So this will make R vector is equal to minus rho A rho plus H A Z. So for Weizsäcker I need ideal R by, this is also 4 pi capital R, you can make it, that's not an issue, right? So I have to find R and ideal I know, DL we have to find, right? So DL is, what is the length? Fine. So we know for cylindrical coordinates, DL vector displacement vector is equal to d rho A rho plus rho d phi A phi plus dz AZ. Fine. Okay. Now we see, you see when you are having a, what do you call, right? So we are having a, if you have this one, this ideal is creating vector R vector in this direction, so it will flow like this, right? So similarly we have another ideal opposite to that, because I have to told every ideal we have to take ideal 1 2 3. Let us take it is ideal n, so this will create vector field in this direction, right? So we know when you have a vector field in this if like this, the resultant vector will be in this direction, and this component will be cancelled, this component will be added. If you have any doubt, please refer my video on basics of vector algebra. I have dealt in the unit number 1. So these two will be cancelled, only this will be there. So this is what my H component, Z component, this is what my rho component, because this is rho, this is also rho, everywhere it is rho component. So rho component is 0, H component is present, right? So what happens in this equation, we can make rho component is 0. So d rho A rho, this is negligible because this is 0, right? So that is one important point. And we can say that Z component is also 0, right? So why Z component is also 0? If there is one positive Z component here, somebody will produce a negative Z component. So Z component will also be 0. We have only this pi component, right? This is what pi we know in cylindrical coordinates. Okay, so we know this will be the pi. So only this will contribute, right? Because my disk is in the xy plane, it is like a rotational. So pi component only will contribute. Already we proved rho component is 0. Similarly, Z component top and bottom will be above the disk and below the disk will cancel each other. So Z component is also 0. So Z component is also 0. We have only phi component. So what happens? DL is equal to rho d phi A phi only. Now we got everything, right? So now we can go and we say that DL cross R, because in Weizsäcker I need DL cross R. So DL cross R means, what is my DL? Rho d phi A phi cross R. R is minus A rho plus H A Z. So if you take a cross product, rho into rho, rho squared, d phi, A phi into A rho, it is minus AZ. So minus, already we have one minus, so it is plus AZ, right? And what is A phi into AZ? A phi into AZ is nothing but, what do you call? A phi AZ means it will be A rho. So it will give rho Z d phi A rho. This is what DL cross R vector, right? So now we got DL cross R. So what is my DH? DH is equal to I DL cross R. DL cross R is given by rho H d phi A rho plus rho squared d phi AZ, right? Divided by 4 pi R square, R cube, right? 4 pi R cube, right? What is R? My R is, where is my R? This is my R. My R is this one. So what is mod R? mod r is equal to r, that is equal to rho squared plus h squared, right? This was modulus of this vector, so that is given by rho squared plus h squared 1 by 2. So mod r is equal to rho squared plus h squared 1 by 2, but what I need in the denominator is r cube. So r cube is equal to rho squared plus h squared power 3 by 2. So I can make what you call 4 pi r cube, that is given by rho squared plus h squared power 3 by 2. Fine. So we know our magnetic field has only rho component and there is no z component. So this part will be cancelled. So I can write dH is equal to right. So sorry, our rho component is 0, right? So rho component is 0. We have right. So rho component is 0. So we can make rho component 0. So we have I into rho squared d phi a z vector divided by 4 pi rho squared plus h squared into 3 by 2, right? So my disk, I have to find integration. This is for 1 dl. It is my disk. For this it is dl. Total means I have to integrate it. Integrate with respect to angle only, because pi is the only thing changing. Angle, not radius or rho. Z is this one. Both are not changing. Only phi component is changing. So integral with respect to integrate both side. So integral dh is h. Integral from pi varies from 0 to 2 pi I rho squared d phi az divided by 4 pi rho squared plus h squared into 3 by 2, right? So what is the thing that will give, you take, it is integration with respect to phi, other things are constant, take it outside. So I rho squared divided by 4 pi rho squared plus h squared 3 by 2 az, you can take this simply d phi, integral d phi is phi, so phi 0 to 2 pi. Okay, so if you simplify this, what will happen? That is giving I rho square divided by 4 pi rho square plus h squared into 3 by 2, 2 pi into az. This will be what you call I rho square divided by what you call 2 into rho square plus h squared power 3 by 2. This is what my magnetic field ampere per meter. So it is the equation for magnetic field at any point in the axis of the disk, right? Suppose if the point is at the origin, if the observation point, right, for example, if the point P, the point where we have to find magnetic field is at origin. See, in our example, P was here. The distance, this is a P, the distance is h. If the P comes here, if the P comes here means it will come here, new P. What is the h value? H is 0 because this is the distance. The distance from origin to P is h. Now P itself is in origin, so h becomes 0. So h becomes 0. What is my h vector now? I rho square divided by 2 squared whole power 3 by 2, that is 2 power 3. So I rho, sorry, A is a vector here, right? A is a vector. I rho divided by, okay, I rho square divided by 2 rho cube A z. That is given by I is h is equal to I by 2 rho A z vector, ampere per meter. This is what equation for magnetic field at the center of the disk, right? This is disk, this is center. If your field point is located here, this is the equation. right? So if the field point is located here, this is the equation. My disk is here, right? So this is the equation for H at any point in the axis other than origin. This is equation for magnetic field at origin. Okay, so that is very important point. You see, there is a beautiful thing. Our answer is correct because H is in AZ direction. Why? We know that as per Majeeth law, the resultant magnetic field should be perpendicular to ideal and perpendicular to R vector, right? So where is our ideal? Our ideal is along, this is the direction, phi direction. So ideal is along phi direction, that is A phi. Where is R? We know R will be in this direction, right? So R is along rho direction, right? So R, capital R is along rho direction, that means A rho, right? So which axis is perpendicular to rho and phi in cylindrical coordinates? So this must be indicates DZ must be in AZ direction. That's what we got, HZ in AZ direction. H in AZ direction. You see, ideal is along. So from the question itself, we will understand. Once we draw the diagram, we must know where will be the magnetic field direction. So ideal current is flowing in this direction. My point is located in rho direction. So surely magnetic field will be in the AZ direction, right? That is, so answer is pakka correct. Okay, and the next point I want to know is how will be the direction of field, how field lines will be there for circular disk. So we can draw like this, right? So I draw circular disk. This is the way current flows. So I drew. Okay, right here current flows like this. This is the way our current flows. So magnetic field lines will be like this. Okay, so let us see. Please adjust. Sorry, I draw properly. It will be like this, right? So it is flowing like this. Here it goes like this. Here it goes like this, right? So, and it is going like this in this direction, right? It is going like this, fine. And here it is going like this. Why? We know that when you have a current flows like this, where is the magnetic field direction? It will be like this. That's what we have seen in the Majeeth's law. So here current goes like this, right? So this is coming, this is going in. So this must be coming out, this must be going in, right? So for this, so all the field lines should go inside like this. Here all the field lines should enter this side, right? So all the field lines should enter this side because current flows in this direction. Okay, because it is going in, right? So similarly here it is coming out. You see what will happen, right? So if it is coming out means I draw the diagram. Suppose it is like this. So it will be cross, it will be dot. We know by its law. So if it is coming out means everything will be coming out this side it should go in. That's what it is going in. So this side it should come like this side it should come like this, right? So here it will go. Now it will go like this, right? So everything will be like this is the magnetic field lines for current loop, right? So that is what we have to know. This is what our circular disk or loop, current loop, right? So I hope understand everything clearly. Please adjust for my diagram, right? So if you have any doubt, please ask me in comment section. I will clarify all your doubts. Thank you.